Já está.
Hi, everyone. Thank you for your presence, for attending this edition of the online CNC meetings. We are here today to learn with Professor Noriaki Ohara. He's Associate Professor of Civil and Architectural Engineering at the University of Wyoming, USA. And we are here to learn about dynamic modeling of snow distribution as evolving probability density function using the Fokker-Planck equation. Thank you, Professor Noriaki Ohara, for accepting our invitation. And to say a few words about our invited speaker, we have with us also Professor Rui Pita Perdigão from C3C, to whom I now give the floor to say a few words about this meeting and present our invited speaker. Thank you.
Thank you, everyone, for coming, for sharing with us this beautiful moment. I am extremely honored to welcome here to Portuguese soil, to the glorious orientation, Professor Noriaki Ohara. He is extremely mathematically oriented. That's why he is here. Fantastic person, huge heart, very sharing, and he has done all his career in the interface between physics, engineering, environmental science, earth system science, and mathematical modeling. So he is a very eminent mathematical modeler of environmental systems. He currently has a great focus on snow modeling. However, the beauty of things is that the methodologies that are used are transversal. They can be used in any field of science, because things like the Fokker-Planck equations have the ability to capture, as he's going to explain, the probabilistic nature of information and the evolutionary dynamics over time in a spatial temporal coherent manner of any system, in this case snow, but naturally applicable to geophysical, biologic, social systems. And it is my great honor to introduce Professor Noriaki Ohara from the University of Wyoming in the United States. And he is an external collaborator of C3C, of the Center for Ecology, Evolution, and Environmental Changes, in particular the Climate Change Impacts Adaptation and Modeling Group, CCM. So he is our guest. He is staying for this academic year as on a sabbatical leave. And he has chosen our beautiful country to do so. It is a huge honor to welcome you, and the floor is yours.
Okay, thank you. Okay, thank you, Professor Perdian. Okay, so yeah, I think a great introduction about my background, and a great honor to be here in Portugal. Now we are in Alentejo, and then that's last couple weeks ago. I think we got the snow here. So snow is not. Snow is a kind of issue here. Could be, that's. Of course, climate is evolving, and never know what's going to happen in the next, So, but it's like he mentioned, it's a methodology is here that we can apply to other programs as well. So let me start the presentation. So, like this. Okay, so this share. So. Okay, so this is a title screen here. Well, let me small my screen here. So, okay, so title is kind of long, but it's to describe what it is, and that's necessary. The keyword is probability density function and the Fokker-Planck equation. So, this is an unusual approach for snow modeling unless you're really serious about the snow distribution modeling. That's the affiliation and everything. Oh, this photograph is taken, by the way, this is taken here in Alentejo. It's a beautiful place, so I'm kind of enjoying the weather and hospitality from Professor Perdigão here. So, where I'm come from, I'm originally from Japan, obviously. Perhaps, not obvious, but I'm from Japan, and now I'm representing the state of Wyoming, United States. So Wyoming is here, is a square, perfect square state here. we, probably you have, nothing about the Wyoming, but we do have the Yellowstone right here. We have an excellent, interesting geological feature like Davis Tower, beautiful mountain of the Grand Teton, and main industry is the coal mine. So that is almost monopoly economy here, and it's very important. All of the state budget, the budget is from this industry. I mean, rather than the, of course, tourism. It's a least populated state in the United States. Lots of wild animal like that. That's living here. And here is the culture is, that's a cowboy state. Cowboy, so somehow I'm teaching, training cowboy kids, but somehow people describe me as ninja. So ninja training cowboys here. So that is the situation right now. Okay, so this is a backyard of my, our campus, the Snowy Range. It's beautiful mountain. We talk about the snow distribution in this mountain as well. Of course, we have some fish, fishery in, these nice lakes and streams. It's beautiful. And winter time we have snow almost every year, but the snow is really not that deep. So that's the kind of picture, but however, almost every year we have a crash due to this lower visibility of the road. And this is the last couple of years ago, we got a huge pileup, more than 100 car and trucks has been involved. So snow is a big issue, much bigger issue than anything else in Wyoming. Yeah, so. All right, so now let's talk about the snow here. Of course, snow is a very important part of the Earth system. So therefore, all the atmospheric model and Earth system model include the snow. Cannot ignore it, okay? But we have, all these snow distribution. And if you look at the detailed observations, a lot of variability, especially in Wyoming. This is just 1 kilometer by 1 kilometer observed snow distribution in the Laramie Range. And if you look at this, this orange or beige color place, it's basically no snow, open, bare ground. Whereas there are some along this valley, we have nearly 7.5 meter deep snow. So it's really depends on where you grab the sample. If you grab the sample over here, no snow, almost no snow in Wyoming, but not true. But if you grab sample here, oh, it's huge snow. It's snowy place. Yeah, however, that is exaggerated as well. And also, this is the grid size 1 kilometer by 1 kilometer is this big, and a lot of variability here. And it's 100 meter by 100 meters, still a lot of variability in it. And this is a typical grid resolution, the GCM and regional model. Hydrology model, it's getting better, but still a lot of variability in the single cell. So that is a topic I'm talking about here. We call the subgrid variability. Yeah, so this is another kind of redundant here. So grid size of weather model is too big. It's still, that's getting better, and it's 20 kilometers. It's still a lot of variability within the one cell, and that's we have to deal with that. Okay, so historically, what how we do? The first approach was, that's like last century. We use mainly, LAMP model. So we just set up the one physical, equation, and then represent the whole entire area. That's called the historical model. But now it's the last 2 decades, we then talk about the, distributed model, and that is considered to be the effective. Yes, it is effective, but it's still not quite for especially Wyoming snow. Well, I think it's probably true for everywhere, I think. So therefore, I'm proposing a stochastic model. We are using, describe all this snow distribution within this probability density function. So x-axis is snow depth, and then y-axis is a probability. So if you look at the probability density function, it's describing the all snow feature in a one single cell. So historically, people use stochastic is a antonym of the physically based, but that's not true here. Stochastic and physically based. So that is something I like to emphasize. This is a fundamental. Let's visit what's the snow dynamics. What we need to know about the snow modeling. Yeah, we have so many energy fluxes. Yeah, so we, when you compute the snow melt, we need to have a energy flux, radiation, short wave, long wave, and of course it's temperature sensible heat, latent heat, precipitation, blah blah blah. So many energy fluxes. So we have to consider about that. And then which one is the most heterogeneous? Which one is the most uneven? That is a kind of fast question to have. And then we talk about the three different, maybe two major models in this presentation. The first one is for my PhD work, and it's a proof of concept model. And then let's move to the other one. So yeah, next slide, and look at all these state variables and what's the source of stochasticity, and we selected two of them. And then first proof of concept model, we selected two random variable, snow depth and snow temperature. And then I selected two source of heterogeneity, short wave radiation, and snowfall distribution. But if you look at the snow distribution, north facing slope snow melt much faster than south face. It's opposite, sorry. South facing slope is much faster. So because of the radiation. So yeah, and also snowfall distribution is very important. So we selected these two as a source of stochasticity. So this model setup, and we need equation. Equation is necessary, unfortunately, for some of you. But yeah, so that's. But it's the first task was that's we need equation. Set up the equation. In fact, that's first ordinary differential equation form of the snow model. I think. Before people use just add and just without equation. Simple regression type of the model was used, for the snow modeling. But this was now it's differential equations, so that we can apply the stochastic technique, stochastic differential equation technique here. So I selected always three equations: snow temperature variation, mass conservation, which is snow depth, and snow density variation, and then top two are the treated as random variable. And the source of the stochasticity is a short wave radiation, and this incoming snowfall and density variation is just deterministic. So that's how we look at the whole system. And then we got the Fokker-Planck equation corresponding. That's looks scary equation. When I saw it first time, I was really shocked and scared. But it's but if you look at it carefully, it's it's not that bad. It's look like a attraction dispersion, attraction diffusion equation. So state variable is now P, probability. And then now it's the time variation of the probability is 1, 2, 3, 4 terms here. One time derivative with respect to temperature, two time derivative with respect to temperature. So this is advection diffusion type equation. Advection dispersion diffusion. Yeah, it's the same thing to me. So the key point is that before we talk about okay, so let's talk about all this. This was we have a stochasticity here, and it is called the stochastic differential equation. So this is truly stochastic now. But once we switch to this form, it's now deterministic equation. So that is a very important transform between two equations. And then this F, this advection is treated, becoming a mean behavior of the snow probability density function. And then D is this diffusion or dispersion, and depending on how you interpret, but yeah, that's basically randomness within a system. So probability density function, how it look like? So if you look at the snow depths, if you have a snow depth, uniform snow depths, basically mean just shifted. So that is advection, treated as the advection. So if we got a uniform snowfall, we got this shift. But if we have a snow redistribution, no input snow, and so there are no mean value change, but dispersion happened. So that is a dispersion coefficient right here, here. And if you have a heterogeneous snowfall, mean value shifted and also dispersion. So that is a snow depth direction. Snow temperature, uniform heat supply, basically shifting like that. And if it's cold, then it's going this way. Okay. Uneven heat exchange, and then we have just diffused. And if we have uneven heat supply, we have a mean value change and also dispersion took place. So that is a kind of give you some idea how this system equation works. And once we have a this deterministic Fokker-Planck equation established, this equation can describe the stochastic system so explicitly. Okay, now let's go back to the field. How the probability density function behave, and yes, then this distribution was extracted, and then it's actually pretty good fit into the Gaussian distribution. That is very interesting. That's the observation. So that's to give you idea how it look like. So that's make sure you know that the x-axis is snow depths and probability density function. Okay. All right. So let's now we have a Fokker-Planck equation to work. Okay. So wow, where to start? Oh yeah. So that's the average mean value. Ensemble average operator is this parenthesis. This is pretty straightforward. It's treated as a deterministic. This is fine. But problem is this time-space covariant. It's including some integration over the time, time and space. That is kind of what to do with it. So that was first. This is the second big problem in my PhD work, and so we needed some simplification. Then in the short, yes, we just shortwave radiation, just delta correlation. Okay, so that's let's ignore about the time direction variability. We focus on the spatial variability only. Okay, so that is basically what the meaning of delta correlation. So it's end up with a variance of the shortwave radiation. So that's it. Okay. Time direction of the snowfall, I use the compound Poisson process. If without the compound, it's like a very standard snowfall precipitation modeling. So basically ignore the spatial direction variability, focusing on the time direction only. So we don't know, we are not discussing, how appropriate this compound Poisson process is, for the snow process, but I just remind you, this is a proof of concept. So, okay, so first we have to talk about this delta correlation in the shortwave radiation. I computed the shortwave radiation everywhere on the field, and then its variabilities come from this angle, aspect ratio, aspect of the topography. If south facing, we have more radiation, north facing much less. And then we computed the spatial correlation. Okay. Wow, what's it look like? It's long memory, long range dependency. So we have to integrate over this area. Well, but it's look at this, that lag size, 30 kilometer. It's huge. So that was a big headache. That's a big problem. So how to deal with that? Well, we deal with the old mean value. It was, in the advection term, but we're only talking about the variability, in a local variability. So let's introduce some grid like that, and then subtract the mean value from this grid, and then basically remove the local trend in space. Then what's going to happen? Then that's what happening is here. So this is the original not auto, but it's a spatial correlation function. We have a long range dependency, but if you subtract 1 kilometer average value, and it's that's losing the dependency quickly, and then after 10 kilometer area mean value is subtracted, length, correlation length, it's becoming really small. So now then when I found this relationship, my advisor, Professor Carlos, congratulated me, and okay, good. So you're good to go. That's all you have to do is just solve it. So yeah, so that's basically that's delta correlation. It's good to go. Okay. Of course, we have to compute the Monte-Carlo simulation. So to check that our method is correct. So we are basically removing all this variability with respect to time. So we have to look at this same distribution, but the trajectory should be smooth like that. So that is a corresponding Monte-Carlo simulation. Yeah. So we did that. Random snowfall compound Poisson process. There's another long story there, but it's Poisson process is like a modeling of the arrival time of the next bus. If you're waiting in a bus station, in next bus, average time, so that's how we model the precipitation, and then we only look at the snowstorm period. So that's make it a compound Poisson process. So that equation look like this, but it's done it. So now we have this particular form of Fokker-Planck Equation. So simplified, much manageable form. It's a variance rather than integrated covariance. And then this is some mean value, and the other nice, beautiful equation. It's ready to solve this particular equation. Yeah, it's kind of like that. Okay. Oh, I use the diffusion here. Okay, so we still need some numerical scheme to solve it. So we set up the old grid, and then use a finite volume method because it's mass of the probability density function is super important. If we probability density total probability density is more than 1 or less than 1, it's not good. It's distort a lot of solution. So we need to make sure this mass is conserved, mass of the probability. Well, that's it. That's what it is. So I use this method, and then flux compute it, and so on. So, but make sure this this x-axis temperature, snow temperature, y-axis snow depths. It's some people couldn't understand why. Well, that is the meaning of this Fokker-Planck equation. So we are solving for the probability density function. Boundary condition also give us a headache. So when snow depth is 0, what's the situation? 0 depth, 0, no snow. What's the temperature of no snow? Well, it should not appear here. So we have to set a no flux boundary here instead of here. So that is a kind of important notice. And then when we have a snow disappear, and then basically the equation vanish when snow disappear. So we have to additional treatment for this 0 point. That is a little trick for this particular case. Okay, so snowmelt rate. Okay, so we have a snow probability density function. What to do with that? Well, how to compute the snow, total snow? As basically snow melt only at temperature equals 0. So when that is we need the marginal probability density function here, and then you can compute the total snow melt amount over the area. So that is how we compute the snowmelt rate. So, all right. So this additional information, attribution time is the flux limiter method, dispersion, central difference, and so on. Atmospheric condition was used in observed data. I selected 3-day period, two cases, melt period and accumulation period. So this is the initial condition. We don't know well, we already saw the distribution is Gaussian. So I set up the Gaussian as an initial condition, and then it started. And then this is the solution. It's a time series, so it's of course it's initial, and it's 6 a.m. here. The Monte-Carlo simulation is look very similar. And after that, daytime, we got probability density hit the temperature at 0. Basically, a lot of snow surface becoming 0 Celsius. Monte-Carlo simulation is very similar. So of course, the Fokker-Planck solution is smoother. And then it's evening. Most of the snow surface becoming a 0 degree. In Monte-Carlo, again, it's very similar results. And it's nighttime, still some area remain 0, but it's that's pretty comparable. And so so this is the end of the simulation after 3 days, and then we have some differences, but we do have comparable results. This is the case one. This is the end of the simulation. Sorry about that. More important thing is, of course, this type of time series. So top one is the solution of Fokker-Planck equation, and then this pink line is basin total snow melt, and this blue line is a mean snow surface temperature. It's probably UC. This is a very distinctive behavior of the Fokker-Planck model, or is some including an integrated upscaled model. Snow melts actually starting very beginning morning time, but corresponding mean temperature is much below 0. So basically, some area start melting before the mean temperature reaching 0. So mean temperature never got 0 degree, but we have a significant snow melt day 1, and day 2 we never reach 0 degree, but we have a significant snow melt, and so that is a very different results from deterministic traditional equation. Okay, of course it corresponds Monte-Carlo simulation. It works, yes. Checking the standard deviation. So of course, standard deviation is important. Monte-Carlo simulation has actually much less standard deviation than the Fokker-Planck equation. And we also selected upwinding, selecting a different scheme. And some of you, at least I was worried about this artificial diffusion in the Fokker-Planck equation. So, but we still have a comparable, there are some differences. Case 2, snow precipitation, we do have some similar results, and then this probability density function looks similar. Again, it's a mean temperature. I think the mean and the standard deviation of the temperature, and this is the snow temperature, and then this is the mean of snow depths here. When we have a snow, and then we got the increase. So that's at least this model behave okay. So that's an important Monte-Carlo simulation. Also got a very similar results. So conclusion from that my first model, my PhD work was published 2008. PDF approach has a great potential for modeling of subgrid variability based on the process-based knowledge. However, the weakness I notice, I'm doing it, so I know the weakness. Numerical error accumulates in the PDF. So of course, especially when the slope of the probability density function is very steep, then its error is not negligible in even this 3 days period. So therefore, limitation computation period should be shorter. And then it's if we simulate all the season accumulate error accumulate, then eventually not very practical. So that was a kind of issue I found in this first application. So now now I got the job here and in Wyoming, and it's completely different era. Now we have a airborne lidar, and we can measure the snow distribution great detail. Although it's very expensive. One flight is nearly $1 million. It's at that time it's really expensive. But we can obtain a snow surface elevation and then ground surface elevation, and then snow depth distribution. So that's a really large dream data set, and we are dealing with it. So excited, and we try to improve, and then let's try it. So that's the results of the light observation. I hope this animation works. Grayscale one is the snow distribution, and then the color one is the true color area photo. So if you see it's a lot of snow variability, in the beginning I show the distribution that's actually come from this data set. So you see it's along the channel we have a lot of significant snow distribution, and also we have snow is trapped by the vegetation. So vegetation surface roughness is actually a lot to do with the snow accumulation. So that is clearly seen. So we have to model accordingly. And second time, of course, we have to check, comparison. LiDAR is correct. We go there and measuring it. This is first LiDAR data set for us. So we just check it, go there and then measure hundreds points, maybe thousands, and maybe and then huge group of people there and test it, and it looks reasonable results. So let's analyze that beautiful data set, and we flew over these two mountain range. One is the snowy range, and then snow depth map, elevation, land cover, Laramie Range, same. But if you deal with everywhere, it's too much, and I selected the 9 squares. So that is we can look like that. So top 4 are the forested snow distribution in the forested area, and then bottom 5 is a partially forested, or it's mainly open area. Distribution is so different. If we have snow, forest, the distribution is more uniform, and then we have a lot of variability there. In this the particular work, we did all the spatial correlation things like fractal dimension and so on, but that's not discussing here. So let's talk about the probability density function over here, and then we see that's a beautiful Gaussian if we have the forest, and then if it's open, it's much less. All right, so observing all this data, and then we selected okay, let's focus on the snow depths. Forget about the snow temperature variability. It's time-wise, it's temporal evolution of the temperature is huge, and it's also a problem. So let's forget about it. Focus on the snow depths, and then instead we introduce much more. So basically, Snowmelt Rate distribution, snow redistribution, by wind and vegetation effect. So we selected three. So additional stochasticity introduced. So that is a second model, very recent one. So this is one-dimensional Fokker-Planck equation. Simpler? I don't know, do you agree or not? But excuse me. Probability, time evolution can be described as a advection dispersion, but dispersion equation is longer here. So that is of course, is a exciting problem. My students are working, was kind of intimidated, but eventually worked out. So snow redistribution and vegetation and wind separated, and then we found that the snow redistribution by wind is really function of the surface curvature. So therefore introducing like this, and so on. Yeah, it's really too much detail. Perhaps it's well, yeah, it's perhaps showing this perhaps better. I think three different components: snow transport, variance on terrain curvature, mean speed, wind speed. That is definitely the one factor, important factor of the diffusion coefficient. Vegetation is also function of the snowfall rate. Snowmelt effect, of course, it's some area melt much faster. So mean snowmelt rate and spatial correlation snowmelt rate. That was actually determined by the independent distributed model and analyze it. And then that's how we end up with. Oh, probably I do have, yeah. So this is a test basin, no names watershed, and that is a little watershed here. So that's snow distribution is observed. And these orange lines are the snow GPL, ground penetrating data. So if you're interested in geophysics, you know what it is. Basically, can measure the snow depths instantly. But you have to drag the sensor. So that there's a poor student drag the sensor along this line here, and we have somehow got the distribution on that day. But that's much less costly than the Airborne LiDAR. Airborne LiDAR is like $1 million, something like that. So again, long range dependency. We have to look at that and then remove our snowmelt pattern, and then we removing all this local mean, and then we again it's end up with it's not delta correlation, but it is Gaussian correlation. So we have some finite memory, so therefore we can integrate this correlation structure. So that was our conclusion for this snowmelt variability things. And then, oh yeah, this is the result. That's exciting. Other times is entire season. Look at this. This is October through the end of the season. This blue line is an observation that we call the repeater tower in the middle of the basin. We have the one sensor here. So we put this one as one of the trajectory in this model. And then this black line is the mean of the snow depths in the watershed. And this shaded area is the 95% confidence area. So we have actually probability density function here, but not necessary to have a Gaussian. So we put some limit and showing that. So our impression, great, works fine. Time-wise, it really works really good for the two water year. This is another year. We do have some measurement there, and then some measurement missing period there, but we really good. And then there are some GPL observation on that day, and then we do have a LiDAR observation in that day. Okay, so this is the comparison of the probability density function. So this red dashed line is a simulated PDF Fokker-Planck model, and this black one is estimated from the field observation. So it's 2-hour observation is pretty good. And as you see, this is a physically based, not too much room to adjust, unlike a traditional model. Physically, we estimate all these parameters, including albedo and all these different things, and we still fit, this good. So we are so happy with this result, especially when we compare against the observed PDF by the Airborne writer in the lower one. It's almost perfect. So I was so happy. And then that was a result of that new model. Just go back to the observed snow depth probability density function. We have a nice Gaussian in the forested area, but I'm curious why we have a non-Gaussian in other places like that. Well, it's most of the the problem is actually come from this zero boundary. Snow depths never go negative. Negative snow depths? No, not possible. So snow once snow melt out and then snow density accumulate at 0. So that is a kind of main mechanism to bring a snow density function non-Gaussian. So it was found all these, especially this open areas. So let's go back to our Fokker-Planck model, and then we plot all this evolution of the probability density function. In a nice period, we have a nice Gaussian, end up with the Gaussian probability central limit theorem. But once we got snow melt, and then that's hit a wall of 0, snow depth equals 0, and then we got a very sharp probability density function, and it is probably the main mechanism for the heterogeneity or the sharp non-Gaussian distribution here. And the Fokker-Planck equation can handle that. Okay, so another beauty of this model is what makes snow less uniform. We evaluate all different terms. My student put a lot of effort to it, and it's found that the yellow dot is that the dispersion coefficient due to the wind, and then this red one is due to snowmelt, and the green one the vegetation. So we found in the this watershed, the wind and vegetation effect is much important, much bigger effect on the heterogeneity of the snow. So snow depth, snow melt, of course, it's contributing a little bit, but several order of magnitude different. So that is our finding for this particular case. Of course, this may not be true for the other watershed, like open area or California or somewhere Alentejo. Yeah, of course, maybe different places, but we based on the physical knowledge, so therefore we can estimate that if we have a sufficient information. So here is the conclusion for Fokker-Planck equation. It's found to be effective for the subgrid variability modeling of snow, and model performance was tested by the Airborne LiDAR and snow GPL data. It's a real observation. That is a important improvement since since my dissertation work. The new Fokker-Planck equation that was published 2019 can be applied over one snow season. So it's ready to apply to anywhere. Yeah, and the entire season. Snow redistribution and snow melt are the main source of the stochasticity causing a spatial variability of snow depths. So that's our conclusion. That's a little news. Fokker-Planck equation was recently having incorporated in the known as rapid refresh numerical weather prediction model and high resolution rapid refresh model. So that is now operational mode. So so national weather prediction in the United States use our model because it's snow, change the energy fluxes in the atmosphere quite a bit because of the high albedo. So that is already operational. So this is my last slide, I think. Thank you. My contact information is here, and that's my student, Siwei. He got a job in NOAA. Then he's implementing his Fokker-Planck model, and then now it's operational. So that's and then this is a publication I mentioned here, and that's the end of the talk. Thank you.
Thank you. Thank you, Professor Noriaki Ohara, for your very insightful presentation from which we have learned. Thank you very much. I invite all of you that are following this presentation, you can leave your questions on the live chat on YouTube on the window that you have on your right. So if you have any questions, please let us know and we can ask Professor Noriaki Ohara. And in the meantime, since we don't have any questions yet, I invite also Professor Rui Perdigão. If you have any comments or any question, please feel free now to say a few words. Hi.
Hi. Thank you so much for your very insightful and pleasant and highly instructive and joyful presentation. It is always a pleasure to see a very honorable colleague coming and presenting extraordinarily complex science in such a beautiful and appealing and a clear manner, making mathematics fun, because mathematics is the most beautiful language. It's the poetry of the universe, and it's the cosmic pencil with which you draw and communicate with nature, and the way you communicate with nature through math is wonderful. And at the same time, it is a huge honor that not only you derive the equations and not only you mathematically compute and numerically as well to validate, but you also go to the field with the instrumentation without any fear, without any prejudice against the experimental part. So a great theorist, a great computational scientist, and a great environmental scientist that goes to the field and collects the data there, touching nature. And this is something that that appeals to the very core of what being a physicist, an engineer, a scientist, a natural scientist is. Never forget to touch nature, to go there, to go with the instrument. The person even carrying it, it's a big honor, carrying it. And in that regard, it is a very, very grateful experience. I am aware of the research, so I don't have technical questions, but I can provoke a little bit while we are waiting for questions from our guests that are hopefully watching. And now let's imagine the following. So we know that you brought the snow to Portugal. We were supposed to have a sabbatical in Vienna, but because of COVID, we are doing an even better place. Theatre is even better. So we are in Portugal, not in Vienna, for this COVID time. And therefore, you brought snow to us. And now, but people may not be so happy with the snow. Now imagine somebody would say, okay, I do lunar modeling on the Portuguese beaches, on the coast. If somebody would come to you, a geophysicist, a coastal geomorphologist, would come to you and would ask, okay, can I apply this also to lunar motions, to coastal modeling? What would be the 2-3 short words of advice that you would give to somebody who would want to model, for instance, sand motion, lunar motion? Just a couple of ideas to such, just in terms to ignite, because there are people from geophysical and geologic and environmental groups, and a lot of people that just want to go to the beach and understand the Portuguese snow, which is the sand. So it's not the same thing, attention, it's not the same thing, because this is, snow is completely different from sand. let's imagine you want to model a granular medium. It's not a fluid. It has certain fluidistic properties, but how would you do it in short terms?
Okay, sure. Of course, first my advice is observe the nature. Yeah, look at the nature and accumulate the knowledge, observations. That's the first things. And then start with some simple process-based equation. I use, first my task was, like an ordinary differential equation form of the Snowmelt equation. It's the same thing, no difference. Yeah. So observe the nature and then keep looking at the nature. That is very important. And especially, nowadays, a lot of new data sets becoming available. So just, keep looking at all this development and observe the nature. Yeah, then try to improve our formulation. Then once we got to some point, and then try to look at, what's the most important thing, what's the less important thing, and then rank it, and then we need to set up some cut-off line. And then if we focus on the most important thing, and then just for now, just leave the less important factors. So that is things. And then we'll focus, this, example that the coastal morphology is somewhat similar to the snow redistribution. Snow is, particle motion in the, fluid. So I'm also interested in the all these processes and river morphology as well. So I'm looking at that problem as well. So yeah, I'm happy to.
Thank you very much. We now have one question in the live chat of YouTube. Is by researcher Vitor Souza, who is actually a collaborator from the C3C. He thanks you for your talk. It falls outside of his field, but he works in population genomics, and they often find problems that can be modeled as sums of waiting times with rates that change in time. So the question by Vitor Souza is the following. Do you think that the compound Poisson process solution or the Fokker-Planck equation can deal with those type of problems where rates change through time?
Certainly, yes. This is of course, it's a relationship, clear relationship must be established. But if it's a relationship is established, yes, definitely we can handle that the evolution of the probability density function of the such problem as well. Yeah.
Okay, thank you. In the meantime, we don't have more questions, but I have one more general question, curiosity, taking into account the research that you have presented here and other projects that you might have in hand. What will be the future challenges that you will tackle in this field?
In snow or?
In snow, or maybe other related projects, research projects that you have.
Yeah, I think
once you can let us know.
Yeah, okay. I'm kind of course, it's morphology, river morphology, and all these things are important, interesting to me. But I'm start looking at the fire problem. So forest fire is a big issue in Western United States as well as here in Portugal. So that's something in a common theme to work on. So that's I love to looking at. So yeah. And
thank you. And that's really a big challenge. Yeah, that's really a big challenge that we have in Portugal as well, forest fires. So yeah, we are looking forward. And I don't know if Professor Rui Perdigão, if you have anything else to add. After that, I would say that we can wrap up our session.
Very good. Professor Noriaki Ohara was mentioning the fire problem. It's actually an initiative that is being conducted. So we are establishing an international consortium. At Meteoceanics Institute is a participating institution to the C3C, And it has nothing to do with Portugal yet, so it is being done in another continent. But it is essentially modeling fire system dynamics. So it is not about fires per se, it is not about fire weather systems per se, but how the coevolution between the fire system and the bio, geo, socio, behavior of the people, the biomass content, the forests per se, the practices, the legislation, and also the climate system dynamics, and all of this in a coevolutionary manner in order to improve decision support systems in practice. So it is something very operationally oriented with dynamical systems approaches to the fire systems. It has nothing to do with the traditional modeling, but it is a collaboration that we are going to do. And I'm very happy to have someone who actually lives up there and sees the phenomenon and hopefully does not get affected by it doing so. A final question. So from a mathematical standpoint, it might be argued, okay, Fokker-Planck equations have been optimized and thought about for Brownian motion-like systems. So systems that essentially have macrophysics, you have modeled the macrophysics, the macro, the envelope of the system dynamics, but at the same time, the macrophysics, the particles are essentially disentangled from each other, which means that you have local equilibrium. So you have overall non-equilibrium, but local equilibrium. So for a system in which you do have these macrophysical connections, so something like a colloid or another system in which you have such macrophysical connections, how would you envision a next step so to deal with this?
Okay, wow, that's a tough question. You know, that's one of the main reasons why I come here to the Professor Brilliant. So I'm kind of looking at, how, I'm just thinking. I don't have an answer to that question, of course, but it's more generalization of the Fokker-Planck equation is required to describe that such a process. So I thought, that the Professor has some idea. So I think that's hopefully we can have some initial kind of idea, scratch, or some we can, we don't know yet. So that's what we're hoping for. So yeah.
This is a wonderful step in the future because he is going to generalize these equations. So now because we are challenging, so we have this formulation, but when you take the nonlinear master equations, so if you have linear master equations, and then you can derive the traditional Fokker-Planck equations, and then when you go to the nonlinear master or anomalous diffusion, there is a generalization, and then we are exploring that. And I'm very excited because I have the right person here. So because these things will have to be validated by touching and being with nature, not just dreaming, looking at the sky, but actually doing and touching things, because mathematics is talking to nature. Oh, thank you so much. I don't know if there are any questions further.
We don't have further questions, but we have people congratulating you for the talk. So we have some colleagues that are also following that are congratulating you and leaving messages on the live chat of YouTube. So congratulations once again. And it was a very interesting talk, interdisciplinary research and applied research. And I'm looking forward also to further applications, as you mentioned, for example, for forest fires. So looking forward and wishing you all success. Thank you once again for accepting our invitation. Thank you also, Professor Rui Perdigão, for being with us. Thank you, Mariana Marques, who is here on the back office, backstage, ensuring that everything goes well. And thank you all that are following this session of the CNC meeting online. And stay tuned for the next editions on the next weeks. And stay safe.